So let's do the second type of Atwood, which is type 2, which would be a situation where we have a horizontal table. We have a block A connected by a string to a pulley and another block. And the question, as we cover chapter 5 and chapter 6 around forces, the question is always or often obtain the acceleration. If the question is different, the method is exactly the same, the algebra is just different. You solve for something else. So, what is the acceleration of the system as we attach two blocks A and B on a horizontal table for A? Let's make it start from rest. Let's be given the two masses, MA and MB. And we're going to assume a massless pulley. This assumption is very important because that's the one we're going to lose. So let's use the exact same technique as we did last Wednesday. We know that A and B have different kinematic variables, specifically their velocity direction and acceleration direction, which prevents us from considering A and B as one system. It's only when they have the exact same kinematic properties that we can consider both as one system, as we did in previous problems, which means that we have to identify and study each block separately. So if we don't know where to start, let's pick in anywhere of those two. We know mass A, we know mass B. So we can choose to start with A, we can choose to start with B. Let's see where that goes. So let's start with B. That seems to be the easiest one because it's very similar to the case of last Wednesday. So that will allow us to review a little bit. Let's do a free body diagram on B. As usual, B is our system. Therefore, now the next step is to identify the external forces acting on it. If we go down the list, the first one that comes to mind is the weight. We have more than one system, so let's make sure that we give them a specific label. So I'm going to call this one MPG or WB. Then the second one that comes to mind is the normal force. This shows up if our system is in contact with the surface or another system. In this case, it is not. Therefore, there is no normal force acting on B. And the third one is any pulling or pushing. In this case, there's a string holding object B. So there's going to be a tension. Let's call it TB for now. There is no mention of μs and μk, the coefficient of friction. Therefore, we can assume safely that friction is not present. All right. Obviously, we have two forces in the same direction. Therefore, as we're going to apply Newton's second law, because we're looking for the acceleration, obviously, object B is going to move down, and object A is going to move right. So as we're going to apply Newton's second law, we're going to be facing only one equation and two unknown. So we're going to be screwed. That suggests that we're going to need to identify and study another system. But that's okay. So let's pick a coordinate system. As usual, let's follow the technique mentioned many times. If the system is accelerated and we know the direction of the acceleration, let's pick one of our two axes such that its positive direction is along the same direction as the positive acceleration. Since we know from physical constraint that B is going to go down, let's pick, say, positive Y down and positive X or right or left, doesn't matter. There's no force in that direction. Good. Now we can apply Newton's second law because we're looking for the acceleration. As we apply Newton's second law, the left-hand side will have two forces, one positive, one negative. The positive one will be MBG, and the negative one will be TB from chapter 2. This will be equal to MA, but since we're doing the analysis on object B, this M has to be the mass of B times its acceleration. Okay? Remind yourself, we talked about this last Wednesday. The acceleration on the right-hand side represents the actual acceleration of the system. G on the left-hand side does not. G is just a stupid constant, which is positive 9.81. And it shows up because the weight is included. So make sure that you differentiate one from the other. G is just a constant, and it shows up in the weight, and it's always positive 9.8. The A variable is the acceleration of the system. So obviously we have one equation and two unknown, the linear acceleration A and the force TB. So we need another equation, hopefully that involves one of the two or both, so that we can combine those two equations and solve for A. So there is no more equation we can obtain from object B, but we can analyze object A. So let's do that. Object A. System is A. Let's identify all the external forces acting on A. The first one that comes to mind is the weight. MAG, down by definition of the weight. Then object A is sitting on the surface, which is the table. That surface is horizontal. Therefore, there's got to be a normal force coming from the table acting on object A. We know the property of the normal force. Its direction is always perpendicular to the contact or the surface. Therefore, it's going to be vertical. And it's always acting on our system. Therefore, it cannot be down. It's got to be up. Let's call it NA. The next contact force that shows up in our list is any pulling or pushing. In this case, the string obviously is pulling object A towards the right. Therefore, there's going to be a force here. Let's call it TA. There is no mention again of mu, S, and UK. Therefore, that's it. Only three forces. So, could you remind me, what do we do now before we write the equation? Is there something that we need to be able to identify? We've been using Newton's second law because we're looking for the acceleration. But obviously, as we're going to write Newton's second law on object A, we're going to have three unknown: acceleration, TA, and NA, which means that the total mode of unknown will be 4, and the total of equation will be 3. Therefore, we toast. However, there is something that we've done last Wednesday that is still applicable, and is always applicable and always required. Otherwise, you can have two unknown and another equation. Every time you have a system that is composed of subsystems connected to each other. Which law can we use to relate X amount of forces from object B with N amount of forces in object A? That is there anything that's common between B and A in those two free body diagrams? And if so, how do we know, and which law can we use? It should be on your notes. We've done the exact same reasoning last Wednesday. Could you refresh our memory about which law to use, and what does this law allows us to do at this stage? Excellent. Thank you, Mallory. Third law. Third law is always applied between systems, while the first and the second is always applied or are applied on systems. And the third law in this case, thank you, allows us to relate T and TB. Now be careful. It is not just the third law in this case. The third law allows us to relate this force TB with this force TB. And the third law allows us to relate this force TA with this force TA. But that's it. It's the massless property that now allows us to equate those two little buggers. Okay, so we need both. Make sure you write that down very carefully, because you're going to have to justify the same way as you justify the simplification of the equation in kinematic 2 and 1D. As you get to that stage, you not only need to call the Newton's third law, but also the property of the pulley, in this case because it's massless, to be able to justify that TA is equal to TB. So as you use Newton's third law and the property of the TB, don't waste your time, state it right there, and then make the changes directly in your free body diagram so you can save one equation. Okay, and again, I'm stressing this out because this is an assumption that we make, massless pulley. Newton's third law is not an assumption, it's a law. But the massless pulley is the one that really allows us to relate those two forces here, which is going to be lost in chapter 10. All right, so now that we have that simplification, now we can write the two equations, and we know that we're not going to introduce any more unknown, except for one. So we're going to have the right count. So as we do pick the last step and complete a free body diagram, object A is moving horizontally in the same direction as T, so I'm going to pick either X or Y, in this case X, along that direction. And this will allow me to write the sum of forces in the X direction being positive T is equal to MA. And this M, since we're doing object A, it gotta be MA. In the Y direction, since we've been clever and chose the positive X going in the direction of the acceleration, there is no acceleration in our chosen Y-axis. Therefore, we know right away that this is 0, which will simplify our equations. And the two present forces are NA and minus MAG. Okay? Now let's count. 1, 2, 3. How many unknown? 1, 2. This is the same. Let's simplify our equation. This is this T, so I didn't introduce any more. A is the same as the previous one, so no problem. The only one that I've introduced is NA. So now I got 3 unknown and 3 equations. Once you reach that step, that's it. The rest is just algebra. The rest is math. The science just stops here. As you noticed, you can even recognize the fact that you don't even need the third equation, because the third equation will give you NA. But you're after the acceleration, so you should be able to get away with only the first 2 equations. So really, it's not even a 3 by 3, it's a 2 by 2. So we can substitute the tension from the second equation into the first one in order to solve for A. This will become MBG minus MAA is equal to MBA. Again, I would strongly suggest you write your math carefully and keep track of your subscripts. MBG minus MAG. Capital A, lower A for the acceleration. And then you can solve for A, and you end up with, what do we end up with? MBG divided by the total inertia, MA plus MB. This obviously has the units of meters per second squared, because MB divided by MA plus MB is unitless, times G, which is a constant of units meters per second squared, confirms that the acceleration indeed has the units of meters per second squared. Questions about this? Is everybody okay? It's actually simpler than one we've done last Wednesday. Type 2 is actually easier than type 1. It is clear that if you do not add any value for mass for MB, then the object A ain't going to move, and specifically is not going to accelerate either. And hence, the acceleration will be 0. That answer confirms it. If you set MB to 0, the numerator becomes 0, the denominator becomes MA, and you have 0 over MA, which is 0, which makes sense. So the only thing you need to add to create an acceleration for both systems is just add any gram or any kilogram to B. As we're going to add friction, then things will change. If there's going to be friction on the table, and if you add just a little bit of weight on MB, this weight may or may not be enough to create an acceleration. Specifically, that weight will have to overcome the maximum possible value of the friction on the table between the table and object A. So we'll see that later on.